Hello. Hello, my dear friends, to our 14th session of DLD Sync. This is a very special session, as every session is very special. But this is especially special because, again, my good friend, Ellen Jorgensen, is on the show. She changed my life 10 years ago when I learned from her what what the next steps in life science are. She inspired me so much to put the questions of bridging the gap between biology and um, digital approaches to DLD. Since then, life science plays a big role at DLD. I think the 21st century, our century, is the life science century. And we all need urgently to get more into it. Mayana Matsukato yesterday said, this famous economist professor, life is in a mess. Our world is in a mess. Let's get different approaches to solve it. And this panel will show you interesting approaches and very fascinating approaches. Ellen, thank you for coming. You're the co-founder and chief scientist of Aanika. Please tell us about it and introduce our great panel. Thank you.
Thank you, Steffi. Always a pleasure to do something with DLD. This session, I sort of consider it a love letter to biology. So many of you may think, when you think of biotech and biology in terms of an industry, the first thing you think of is biomedical. But we're here to show you that it is ever so much more. It is being used in many, many industries where you never would think it was. And it's also kind of on steroids right now. So I have three amazing people that I've invited to be with me. I'm going to let them introduce themselves right now. The first is Dr. Drew Endy, who is at Stanford. And just say a couple words about your background. You've really been one of the leaders in the synthetic biology field. You helped develop the field.
Ellen, thanks so much. Can you hear me okay?
Yeah.
Oh, it's great to see you this morning, and hello from California, and thank you to DLD for inviting us all together. I'm an engineer, and I work, my day job is as the associate chair of the bioengineering department at Stanford, where I have responsibility for all the education programs, the undergraduate major in bioengineering and the graduate programs and everything like that, just the operation of that. I also have a lab. I've been here for about 10 years now. Before that, I was at the MIT in Boston, near Boston. And over that period of now 20 years, I've been working in synthetic biology. I think, Ellen, what I'd like to offer at the opening, because what follows me is so beautiful and amazing, is just a introductory sketch, a big picture sketch of how an engineer in the 21st century thinks about biology. And by engineer, I want you to imagine not a biomedical engineer or biotechnologist. I want you, like, my first job as an engineer was with the train company, with Amtrak, as it's called in the United States. I was a construction management intern working out of Philadelphia, watching piles being driven in to protect bridges from barges and stuff like that. So I want you to imagine being a young engineer, right? A construction engineer, a civil engineer, a structural engineer, who likes to tinker, who likes to build, and what the viewpoint is with respect to the living world. So just to give you some sketches, biology exists before us. It's not like silicon computers, right? Silicon computers are something that we've constructed, but the living world exists before modern engineering as we know it. And so we inherit 3 billion going on 4 billion years of incredible magical stuff that we still don't understand completely. But we know it's amazing for sure. There's no debate that living matter, see how I'm using that funny word? I'm going to start talking about life as living matter, as a type of material. It does these incredible things, and it does these incredible things at a planetary scale. So what do I mean by that? Well, what powers life? Most of the power, literally the energy, is photosynthesis, coming from the sun and being harvested by photosynthetic organisms, plants on land and microbes in the ocean. And we can quantify that. And so we know that life is roughly harvesting 90 terawatts of energy at any moment. You can think of a light bulb as being 10 watts or 100 watts. Now imagine 90 terawatts, right? That's 10 to the 12th. A terawatt's 10 to the 12th watts. Is that right? Yeah.
That's a lot of busy organisms.
It's crazy. So how crazy is it? Well, how amazing is it? Civilization, all of human civilization roughly is running on 20 terawatts. Okay, so living matter, the living matter on Earth, 90 terawatts, and human civilization is 20 terawatts. So what that means is life is powered today, right now in this moment, by about 4.5 times what all of civilization runs on. What does life do with that energy? It's not gratuitous Bitcoin mining. No, it's taking that energy and using it to organize atoms and molecules into matter, right? Fixing carbon from the atmosphere, taking nutrients from the soil, recombining that with water and other inputs. What's that?
It's manufacturing.
Yeah. So we've got a planetary scale manufacturing technology. It's a natural nanotechnology. It's running at about 5 times civilization. And so right there, just the back of the envelope, we should all be going, if we could figure out how to partner with living matter to make the things we wish for, we should be able to provision for 10 billion people without trashing the place, without causing ecosystems to collapse. Like the back of the envelope physics, the napkin math looks really, really good. And there's one other thing about it that's incredible. It's already distributed. So biology is most places. It's not like you have to have a centralized factory that concentrates inputs and has the byproducts of intensified production and then logistics and transportation costs. Well, no, what if you could make it where you need it? So if Apple Computer is currently the epitome of a regime of industrialization and logistics, which is designed in California, made in China, shipped everywhere, biology and building with biology represents design it anywhere, design the DNA code, the instructions for the biology anywhere, and to the extent that can be shipped as information over the network, you can grow everywhere. So instead of design in California, made in China, it's design anywhere, grow everywhere as a new way of thinking about how we complement existing ways of making. So maybe I'll just stop right there, Ellen. I'm happy to, unless you think there's something else I should offer at the open.
I think that you brought up 2 themes that I think are going to be a thread through this entire conversation. And one of them is sustainability. And just this, and the other is the idea of distributed manufacturing. And also touching on how we've advanced so much through fields like synthetic biology that we are allowing different players into the field rather than just doctors and people with PhDs. And that really brings me to, I'll briefly talk about what my company is doing. So imagine the supply chain, okay? I think all of us have been hyper aware of the supply chain recently because of all the disruptions that COVID-19 has caused. So how do we be more transparent about that? How do we, for example, trace back contaminated lots of food, or make sure that the gloves and the N95 masks are really coming from reputable dealers? Or how do we make sure that if we want to only buy from, say, producers who are using sustainable practices, that can be somehow traced? And normally that's done with packaging labels and barcodes and things like that. But they stop short, particularly the first mile of a supply chain, which is often in an underdeveloped country, under circumstances where there is a tremendous amount of variation, things like temperature, humidity. And so Aanika has a really unique solution, which is we have microbes that are like little living barcodes. We stop them at a stage where they're dormant, and we sort of coax them into that dormant state where they stay there forever. But as you well know, Drew, we can now basically rewrite the code of life in almost any way that we want to through the power of the technology that's come around DNA. And so just to slip in an innocuous barcode that has no functionality allows us to track and trace things that we never could before. And so if you imagine palm oil, say you want it to come from only a source that's using sustainable practices, because palm oil production is one of the most least sustainable agricultural productions. It's decimating the orangutan habitats, et cetera. Or a lot of corn or soy. It's very hard to label those things except by mixing extremely minute amounts of these edible microbes into them. And then there's also the intriguing possibility of added functionality through things like biosensors, or even using the technology in testing equipment of some sort. So there's like a whole sort of field of things that are so small that we can't see them that can do all of this incredible work for us, that is opened up because of these fields. So my work is mainly in stuff that you can't see, is in minute quantities, but provides huge value. I want to introduce the next person in our dream team here, Suzanne Lee, whose work is the opposite, and who is the person who developed and runs a wonderful conference called Biofabricate that celebrates all sorts of work on the macro scale that relies on biology.
Thanks. Hey, Ellen. Hey, Drew. Thank you so much for the invitation to join such prestigious company today. It's awesome to be having this conversation. You know, as you mentioned, Ellen, my background's so different from yours and Drew. I'm not a scientist. I have no scientific training. I'm a fashion designer, fashion textiles by training. However, my life changed 17 years ago when I had a conversation with a biologist in an art gallery. And that was at a time when I was questioning the future of my industry and specifically trying to understand what are the new technologies or science that could actually assist us in thinking about a more sustainable future for the fashion industry. And it was Dr. David Hepworth, who's a UK scientist, and he proposed to me this vision of biology where rather than growing a plant in a field or an animal for its skin, we might actually harness a microbe to produce the building blocks of nature for us using fermentation. And the vision he painted for me was one of a garment literally fermenting in a vat of liquid, of nutrient liquid. And it just blew my mind that was even a possibility. And then so that's actually how I discovered the field of synthetic biology, because what I learned was if we can then design and engineer an organism to produce something like a fiber for us, to your point, we can start to engineer in functionality that really kind of speaks to our needs, but perhaps wouldn't ordinarily be there in the natural organism, and opens up all kinds of, you know, I think very compelling opportunities to save on the use of land, water, pesticides, and so on. So for me, coming from the fashion industry, that's what got my attention about synthetic biology. My work actually began with a project called Biocouture. That feels a long time ago now. And that brought me to come to work for a biotech startup here in New York called Modern Meadow. And I was the chief creative officer of Modern Meadow for 5 years. And Modern Meadow is a company that also believes that rather than grow an entire animal for its hide, we can harness an organism like yeast to produce collagen, to engineer advanced materials that go beyond what nature has to offer. So that was an incredible opportunity to work in the lab side by side with scientists really sort of advancing this field. And then today I now work full-time at Biofabricate, and we support an international network of material innovators who are building with biology, not oil. And we work with material startups and consumer brands and investors to bring these materials to market faster. So what I have for you today is a short series of slides, if I may, that actually show how this is coming to reality. So this isn't just academic. This is actually changing how we source and design and manufacture the products all around us today. So as we move away from inputs from the petrochemical industry or from animal agriculture or traditional, agrarian type systems, we're moving towards these cells as being our factories. So yeast and bacteria, algae, fungi, mammalian cells become the producers of new materials for us. If we can go to the next slide, I'm going to quickly take you through, some of the way this works, some of the applications. So this is very simplistic, and I know Drew will have a lot more to say around this. But very simply, we're talking about that living matter being fed a nutrient, and then we are waiting for a period of time, but the outcome can be something which is a natural protein or a natural carbohydrate that we can turn into a powder or a fiber or a yarn or directly into a material to make shoes, garments, accessories, the things that we're very familiar with, but just coming from a very different source. So we go to the next one. I want to quickly show you, this is actually one of the world's first products that was launched at the end of last year. It's a Japanese biotech company, and they're making a synthetic silk using bacteria rather than a spider. This is a high-performing ski jacket, which is, really an advanced fiber, but it is fermented, and actually they call it brewed protein. That's actually their brand name. So, this is a kind of real vision of how these materials will start to enter our lives in familiar ways. So it's going to function like a traditional ski jacket, but its origin is completely different. It's the subject of biodesign, bioengineering, and biomanufacture. The next one, the same company, actually. This is again Spiber in Japan, working with Lexus on a car seat. So thinking about these advanced proteins, how can they bring additional functionality to things like the automotive industry? So this is a prototype. The next one. This is something that had a lot of publicity. So we're starting to see established luxury brands and designers. This is a Stella McCartney collaboration with a Californian startup called Bolt Threads. And this is looking at an alternative to animal leather that is derived from mycelium. So mycelium is the root system of fungi. So this is a mushroom leather. They call it Milo. Again, this is a prototype, but these materials are currently scaling up so that they can reach the sort of order of production that is in the sort of hundreds of thousands of square meters every year. So that's actually how biology is going to be coming to market and becoming a scaled commercial reality. If we go to the next one. This is actually representing a project by Ginkgo Bioworks, which is obviously one of the companies in this space that really are bringing these technologies to the forefront in quite magical ways. And this is thinking about using an organism like yeast to produce something like a fragrance, a perfume, but a perfume that perhaps we've never smelt before, because actually it's the product of an extinct flower that through synthetic biology, we can bring once again into being. So I think there's an interesting provocation there for us from Ginkgo Bioworks. The next one, if we can have the next slide. Thank you. This is, and I wanted to also speak beyond fashion, sport, and beauty, where a lot of these technologies are first finding application. One of the most carbon impactful industries on the planet is construction, with around 40% of carbon emissions. And as we look at materials like cement, their nature has been this incredible engineer. When we look to structures that occur in the marine environment, for example, like coral. So this is a company in North Carolina called Biomason, who are able to manufacture incredibly tough construction materials using bacteria in ambient temperatures without needing to fire the material. So this is, again, an incredible opportunity that biology is showing us for construction. And then I think I have one more. Yeah. And I put this one in because this is a local company to Munich, which I know is the sort of home of DLD. This is German company Amsilk, who've been working with Adidas to produce a performance fiber for sports shoes. And actually, I'm also wearing, I don't know if you can kind of see this. This watch strap right now is made by Amsilk for Omega, the luxury watch brand. And this is not leather, not a cotton fiber, but it's been biodesigned, bioengineered, and you can go and buy it today. So when we talk about these technologies, we should know that actually it's beginning to enter the marketplace. These are not fictions. The prototypes are beginning to scale and become a commercial reality. So that's where I want to leave it as a point in time as to where we are now.
Yeah, it's amazing. It's almost like concept cars, and then the things filter down into the cars that you buy every day. It's kind of the same pipeline, except with all of this great biomanufacturing. Well, now I think we're going to go to the largest scale, which is my friend Mitch Joachim, a brilliant architect who founded a company called Terreform 1, which is a nonprofit architecture company. And so Mitch has been interested for a long, long time. He was actually instrumental in some of the early stuff we did at GenSpace. And why don't you take us to the biggest scale, Mitch?
Yeah. Thanks, Ellen. Hi, Drew. Hey, Suzanne. Good to see you guys. It is a superstar panel, and it's great to be here on DLD Sync. I guess, yeah, just a little bit about my background. It's, I think 2000, I met a guy named Oliver Medvedik, who became my roommate at Harvard. And he was a molecular cell biologist there at the medical school while I was doing architecture at the design school. And we had a lot of these crazy fantasies, not fantasies related to a different kind of biological activity. And although those other fantasies are fine too. The idea, though, that it's come so far in 20 years, it is absolutely astounding. Certainly a big moment in our lives was meeting Ellen and seeing what was happening with GenSpace. We're in this very creative building in Brooklyn, the Metropolitan Exchange. There were so many awesome people involved there. I mean, I know you guys were there. Suzanne, I know you were there. There's just, it was just this renaissance moment for biology and design and the application of it everywhere. And going to show some of those things that we had produced from that time and what we're doing lately. I guess also I do have scientific training. I have a PhD in computation from MIT, but my work there was essentially on, ironically enough, concept cars or how mobility would change cities. So definitely a different perspective, and who would have guessed how far we've come on what's happening with not only movement, but waste, energy, water, food. All of these things have been shifted. And biotech has been a major influence in how we think about the urban environment. So maybe I'll just show a couple of slides there. If I just put this up. Can you guys see that okay?
Yes.
Yes, okay. So we think about the near future of our cities. This is 42nd Street, where we create a socio-ecological city that's as green as possible, especially in times post-COVID. We need more open space. We need to consider air quality. We need to consider where we get our food. Other things we were working on were maps of the world made with modified, and this was at GenSpace and with some other groups, modified E. coli to be bioluminescent to show population growth over time. And we had a lot of fun drawing details of cities and learning how to draw with E. coli, which was very difficult to do. And then create these stencil systems and CAD files that would calculate in a very analog fashion with live colonies of E. coli, the exact population growth of all the cities on the Earth as one contiguous organism. So we produced this biocity map that projected population growth to roughly 9 to 11 billion people on this planet, and did that through synthetic biology. Then we work with these guys. Every project we take on has a living organism. So we work with crickets. We actually modified their guts to their gut probiotic to induce vitamin A. And the point here was to make crickets so you can eat as an alternative food source besides cows. Why would you do that? Because there's 2,000 gallons less water for the amount of meat you get from crickets. And I'm talking cricket powder versus something like cows. So we produced this cricket farm and shelter that looked at these modified crickets. It's a GMO insect. I know that's very difficult to get people to eat those two things, let alone, or as individual things, let alone together. But we have produced a farm that you would harvest crickets at a high throughput volume. They die naturally, so we're not killing them after 6 weeks. They live inside these wonderful systems where they get past survival mode, and they actually can enjoy their life, and they reproduce and spread their genetics throughout the entire shelter. And they do that in these pods that you can see here. We also looked at food and cellular agronomy, or producing food from cells as opposed to saplings or seeds. So here's the urban farm pod, where we're doing essentially DIY test tube gardening. Also growing food through the sub-irrigation system, and this is wheatgrass, it's on the outside. But the concept here is to have a relationship between where your food comes from and what you eat. Change that pasture to plate model that we're used to. And then a project we did with GenSpace and iGen, which was rethinking chairs for the future. And that was a lot of fun. We had a poet lead this project with a team of scientists and industrial designers. But this is the entire history of chairs in one slide, and we end in the 21st century, where we think about growing our chairs. And we did this by combining two different systems, essentially Acetobacter that would express chitin and to make it hydrophobic, and cellulose mycelium. So it would be combined with it to make a biopolymer for seats. So here's my daughter sitting on one of these chairs. It's a chair for her kindergarten, and it's a chair that you can eat. The idea is to tell your parents that we eat our chairs in kindergarten. It's okay because we can now grow them using biology. We do that in the lab. Here's a larger version for the big people, adults, made with plyboo, and then there is a triply curved surface on the top made out of this mycelium acetobacter substance. Also looking at architecture itself, where we're growing or changing the base morphology of woody plants to take on shape geometries. We do these in these bioreactors where we grow the roots of plants and then fold them over scaffolds to make homes where there's no distinction between the house and the landscape itself. So it's a completely integrated symbiotic relationship between homes and landscapes. So it's It's an organic architecture, very different than Frank Lloyd Wright's idea of organic architecture, which was still concrete, glass, and steel. And then here's just 2 other projects. We were looking at what's happening with mealworms. They eat styrofoam. So here is a creature you can find anywhere, very popular, easy to farm and harvest. They actually absorb polystyrene naturally into frass, which is, I guess, their own excrement. Then they eat their own excrement and process it again. And you get, from styrofoam, you get compostable mulch. As completely green, be used to make your garden. So we have a project that's being built now for the city of Camden, New Jersey, where we have these biodigesters where people donate their e-waste, their styrofoam, they throw it out, and they could watch it be digested by hundreds of thousands of mealworms. And then the last project I just want to touch upon is what we call design against extinction. Right now we have the monarch butterfly. It's native to New York, and they're dying off because we destroy their habitat. We don't pay attention to their biology. Here is a system that looks at their different stages of life, from eggs to larvae to caterpillars to chrysalis to eventually full-blown butterflies. We designed feeder systems for them, areas for them to get milkweed, all integrated into the building. Looked at the types of foods that they eat, what they're attracted to. These butterflies and many other types of butterflies became our clients, and we designed systems for them architecturally so that they'd have these sanctuaries to give them a chance at life. Lost 90 million of these creatures in the last few years. They're going extinct. The U.S. Fish and Wildlife Services is asking everyone to do their best to try and save this charismatic creature. We're integrating it into facades of buildings, double skin facades, where we have areas for mud pools because they like to take mud baths, areas for nectar feeding, moss areas for air quality. This is an actual full-scale version of that facade for the Cooper Hewitt Triennial, where you could see the butterflies live inside this sanctuary, and they thrive, and they can go in and out and rewild the city of New York. So they're not trapped in there, but they're free to move about their business and do what they need to, and keep these rare creatures alive. And we think it's just absolutely important that architects have a say in how wildlife is treated, especially in urban environments. So that's just some of the things that we've been up to, where we think about biology almost at all different scales, and how architects and designers could have a key role in keeping our cities resilient and keeping them green, which is absolutely crucial. We have 8 years since the United Nations has given us a kind of a platform to get greener or not survive. So that's just some of the work that we've been doing at Terreform One. I love to be a part of this conversation.
Thank you, Mitch. I mean, your stuff is always so visually stunning.
Thanks, Ellen.
It's really interesting how this current pandemic has kind of pulled the curtain back on so many things that are wrong with our society, so many challenges that we're facing that we've swept under the rug. We've been talking about the need for more greenery in cities for years, but until we were in lockdown and realized how awful it was in urban environments when there's no place you can go, because at least in New York City, a lot of the parks were closed for safety reasons. And it's terribly unhealthy. But in the bustle and the hustle of our daily lives, we sort of push it to the back the same way a lot of us say, well, so I'm only getting 5 hours sleep, big deal, I'll make it up later. And it eventually takes a toll. And then this idea that we're cut off from things, cut off from supply chains, cut off from being able to make stuff, and also that we're sort of trapped in our own waste in a weird way. It would be nice to be able to eat your chair or compost your sneakers when you're done with them. One of the things I wanted to ask Drew, particularly, and I'm sort of blindsiding you with this question, but how do you think, what is the potential of this new biotech to make things more equitable, not just biomedically, but across all sections of society, that the sort of things that we're seeing now? can it contribute in any way to even racial justice? I mean,
Yeah, Ellen, thanks so much. I mean, the short answer to your question is it has to. It has to, right? And I'll come back to that. But before I do, I just want to acknowledge Mitch and Suzanne both, but Mitch in particular, your Fab Treehab project. I remember long ago seeing that for the first time back when we were just spinning up the synthetic biology working group at MIT, and was so inspired and blown away by that project in particular. And just want to acknowledge that and give a shout out to the sort of the yin and the yang of dream and technology and design and culture. Really grateful for both of your work, and Ellen, yours as well. But just since I've never had a chance to say that aloud, really wanted to, I was just reminded of that and wanted to speak truth.
Thanks, man.
Hey, Ellen, right. So yeah, of course. I mean, look, Ellen, we're all biology, right? And so when we think about 21st century biotechnology, 21st century biodesign, 21st century bioculture, you know, who needs to play a role in shaping that, and who gets shaped by it? And I think you can abstract biology away from this and just say, well, who gets to be part of society? Who gets to play a role in shaping things? And so the way I think about it is, what does it mean to be a citizen of the 21st century? And what capacities should be available to all citizens as an option? So for example, what I mean by that is I would prefer somebody else who's much better equipped than I am to do something for me because they're an expert. But I might need to have the option of doing it for myself so that I have a healthy political relationship with everybody, right? So this is about not, this is basically about access to capacities, right? So if you have the option of accessing the capacities needed to have a flourishing existence, then you have a chance of being a citizen. If you don't have the option of accessing the means of production, you're at persistent risk of being oppressed politically. And we all are. And so I'm drifting far away from biology, but I'll loop it back. Many people may have heard about things like universal basic income, like that people should just have an income. The problem with that, the limitation of that, is it reinforces one's standing as a mere consumer in a society. So that needs to be complemented by a discussion about what are the universal basic capacities that all citizens should have the option of accessing so that they can be a contributing member of not a sustaining civilization, but I would say a flourishing civilization. Now, why does this matter for biology? Again, and Ellen, you filled in a gap I missed in my opening, right? So I was talking about biology as operating at the intersection of energy and stuff, joules and matter. You teach us that it's also operating at the intersection of information, bits, right? So we've got this stuff, this living matter that's at the convergence of joules, bits, and atoms on a planetary extra civilization scale. And so, oh, wait a minute, now we've got synthetic biology and all of that. What does that mean? We're expressing human intention into living matter. We're inscribing our designs, our ideas, our wishes to the extent we can with ever better tools into this stuff. That's a form of expression. You could say that's a form of speech. I'm really comfortable calling a DNA synthesizer a printing press for genetic material, which is the instructions that operate life from the inside out. So how should we think about our relationship with this politically and culturally? Depends what your values are. And I am much more interested, for example, in debates not about GMO foods and are they safe or not, but not that those aren't important, but rather things like, well, what do we want our relationship to be like with the living world? What do we wish for in partnership with biology? And how does that relate to ourselves? And what type of society do we wish to construct? Do we wish to continue on with Western democracies? In which case, maybe we need to update some of the fundamental conversations around relationships between citizenship and technology. So anyway, that's more than enough in response. How about that?
That's quite a bit. And this sort of, now I sort of understand why you started the Free Genes Project. So just give a little tiny bit about that.
Well, I mean, who owns biotechnology? And I'll give the gentlest perspective on this. It's good to have options. So there's some forms of technology where you want them to be very clearly owned by a small number of people or institutions. And patents are one way of doing that. But there's also the idea of the commons, the commonwealth, and the public domain. And especially when you start talking about languages, well, who owns German or who owns English or Mandarin, right? And it's a common good. And if you're of the opinion, as I am, that we're bootstrapping languages for expressing our intentions in living matter, the genes, then that language is either going to be a free to use language or it's going to be a pay to use language. And I'm actually pretty optimistic about it becoming free to use eventually, because all languages become free to use except for the cost of learning the language. I don't have to pay a fee to use the word. I just get to use the word once I understand the word. So the Free Genes Project out of the Biofabricate Foundation, which is a charity, is basically working to build the technology to make biotechnology free. Officially free, as opposed to just because most of the tooling and infrastructure around industrialization and translation of biotechnology, all the legal technology has been optimized for making things owned, making things proprietary. And I'm not against that per se, it's just nice to have options. So the Free Genes Project, we make genes from scratch that people want. We build that DNA with partners, and then we give it away through an open distributed network that allows for those things to be. An example would be with lots of input and partners, we've made the genes encoding the enzymes used in the COVID-19 diagnostic kits, and we're shipping those DNA instructions in forms all over the world, to Ecuador, to CDC in the US. You name it, we probably shipped hundreds of those kits out just to help people pre-position materials for doing local diagnostics. But it could be local making, right? Blah, blah, blah. Yeah.
Yeah, I mean, Aanika has been involved in that as well, because they very graciously allowed me to be part of a collaborative effort to develop an open source COVID-19 test. And part of our group is working on the Open Enzymes project, which is using some of the DNA that you've been printing. So it all comes a circle. So I guess in a few minutes, we probably should open it up to audience questions. But I just want to circle back to Suzanne and Mitch and ask them what would be your fantasy ask for synthetic biology? If you could ask Drew and me and other biologists to create anything that you would want, do you have a specific thing that you've been hankering for?
I don't know. Can I, if I may, Mitch?
Yep.
I think one of the things that we're obsessing over a lot is that if we shift the production of consumer materials away from oil towards biology, largely using fermentation, what does that mean in terms of sustainability for the feedstocks, the nutrients that we need to feed these organisms? It's still a living organism. It requires a nutrient source. Right now, the majority of those nutrients come from sugar. But I think that there's a lot of work to be done as we think about scaling fermentation for all of these industries and materials. How else can we, really optimize organisms to accept feedstocks that are no longer sugar-based, but rather using things like greenhouse gases? And I know that this is just a sort of an emerging field. But like powering these systems still requires nutrient from somewhere. So sugar still gets grown in a field and has implications for food. So rather than the end product, I'm really interested right now in the different feedstocks and what is the most sustainable, efficient use of waste that we can do to shift that from sugar to something that actually maybe removes carbon and uses carbon as a source of nutrient.
That's go ahead, Mitch. Sorry.
Yeah, that's a brilliant answer, and it's also a really difficult question of if there was a wish from synthetic biology. I might have one word: shelter. I think that issues of poverty, homelessness, the differences in income classes in America, actually across the globe, is just unacceptable and profound. And it's one of the grand challenges that the United Nations has been tackling for, I guess, since its inception. Shelter, how it's produced and based on the capitalocene, who owns it, and ideas of property, all of these things are highly problematic. And I think they come from an industrial age that just, to me, is no longer relevant. And I'm not bringing up utopia, even though I think utopia is a very relevant kind of research inquiry, because everyone in every culture for 2,500 years, no matter what religion or background those people have been looking for a better place. Utopia has been that dream. But it's predicated on the idea that we can produce somehow, I guess, a form of manufacturing. I mean, everything on this planet came from cells. It's all from biology. So if we can get shelter to be created where it is at a positive gain model, it's not something that does zero damage, because that's not going to work. We need something that is going to clean the pollution that's already in the air and in the water. It's going to change the kind of our effect on climate dynamics. And I think what architecture or what happens in cities is an enormous amount of carbon loading in the atmosphere. And we can't accept this number. What are we at? 413 parts per million, the Keeling curve. I mean, we have to reverse that. We've got to do it quickly. So shelter and all of that implies, from facade systems to structural systems to flooring to anything that's in there. And I think synthetic biology has been definitely encroaching upon this field and gaining a lot of ground.
All right, Drew, how are we going to solve all those problems immediately?
Yeah, those are two great, brilliant comments. Let me take them in turn, right? So one of the most exciting, so first off, the examples of mycelium-based circular bioeconomy, right? Growing products that people can use from wood fungus, from mushrooms, starting with inputs that are wood chips, for example, right? Is absolutely amazing, right? And a fine example that is underappreciated, I would say, right? So why the Department of Energy is trying in the United States to take woody feedstocks and turn that into ethanol is baffling, when you could take these inputs and make higher value products. So anyway, on top of that, Suzanne, back to your comment, the work coming out of Germany and Marburg, Toby Erb's work at the Max Planck, many other places where you can basically use synthetic biology to engineer microbes to grow on formate as opposed to sugar. And the decades-old work where you can take electricity, you can take a kilowatt hour of electricity that could be sourced from a photovoltaic panel, split water, fix atmospheric carbon to make formate. So now you can have what I would call an electrobiosynthesizer, where you go from a kilowatt hour of electricity. Right now, it looks like you can get a gram of biomass, but the estimates when I talk with colleagues in chemical engineering here is we can probably push that up to 30 grams of biomass for 10 cents of electricity. So this is unbelievable. And the significance of this macroscopically is it takes that ceiling of 90 terawatts, which is the natural photosynthesis, and it removes it. It's just, to the extent we can generate electricity, we can do biosynthesis wherever we can get the electricity. So that is easily one of the most exciting inside the crucible of the tech things that's emerged and really looks promising to me. Mitch is talking about in these questions coming in from the audience, like how are economic systems designed into the innovations and so on. These are, I have no doubt we can deliver on the nerd rapture, because that's what the last 20 years is demonstrating. Like, we're bringing it. The science and technology of synthetic biology is advancing. It's very much up for grabs about whether or not we can deliver on the culture and society that we want. And the simplest thing to say is that the institutions we inherit, which were optimized for conditions of scarcity and to maintain social stability under conditions of scarcity, those are the institutions which are organizing the labor that is shaping the form of reality, technologies that are enabled by synthetic biology, whatever they are. And so if you have a wish for a particular public interest in the future of biotechnology, then part of the conversation has to be, how do we shape and sculpt the public investments or the public interest investments within this future such that we get the things we want? It's puzzling to me, for example, that Greenpeace doesn't have a biotechnology investment arm. It's puzzling to me that the European Union doesn't have the European Life Agency that is spending public treasure to construct the biotechnology the citizens of Europe wants. You have a European Space Agency. Why not the European Life Agency? And if you don't complement the private markets, which are very powerful and effective at certain things, with other ways of organizing capital and people, then the only thing we're going to get is the ways we know people and capital get organized, produce. And so it's very much up for grabs in this decade, and the game is afoot, is just the macroscopic opinion I can offer.
We have another question from the audience. Which industries that don't have as much traction could benefit most from the biological revolution? I mean, I've been amazed at the reception that Aanika's got with companies that often are large and move like giant oil tankers when you ask them to change direction. For example, we're working with De Beers to actually label diamonds because there are various economic reasons that you might want to know exactly where the source was, in addition to, of course, sustainable practices reasoning. But that's an industry that you never would have thought of in terms of biotech. Are there any other industries out there that that you think would be a really good fit? Again, I'm putting everyone on the spot. I mean, Drew, you've often said, actually on your webpage at Stanford, keep synthetic biology weird, which is a play off of the Austin, home of South by Southwest motto, keep Austin weird. And so what exactly did you mean by keep synthetic biology weird?
It's a stake in the ground reacting to industrial capture. Daisy Ginsburg out of London made this observation a decade ago: is synthetic biology revolution that must promise to change nothing? Or if I was explaining this to my mom, I'd be like, hey mom, we made the living world fully engineerable, but everything stayed the same. And that's sort of what has been a hallmark of the last decade as capital has poured into the marketplaces enabled by synthetic biology. And I'm not critiquing that per se. I'm just acknowledging if that's the only thing that's happening, that's the only thing we're going to get. So I think the question can be reflected back by saying, what does biology touch upon? And we've heard from Mitch and Suzanne and you, Ellen, that the answer is approximately everything we care about. On geological timescales, on fashion timescales. Stuart Brand and colleagues, the paste layering on all those timescales. And so what are the industries, operational mastery of living matter can touch upon or disrupt, or, it's like, well, maybe you should flip the question around and say, what's it not going to impact?
Not going to hit.
One of the ones we haven't touched upon that I'll just acknowledge quickly is education and learning. When if you're a parent or might be a parent in the future, and you think about what the future is going to be, including or not, you always have this interest in securing advantage for your lineage. I'll use that strange language. And so you expose your kids to the things that are going to be part of the future, maybe, if you can afford it, if you can do it, right? And so parents and education had a big role to play in the advancing of the personal computer and things related to that. And so I would say the educational markets, the educational industry is a big area ripe for 21st century genetic engineering to make a contribution.
We need more brain spaces, don't we, Drew? Don't we need more funding? You know,
we need more distributed biotech.
Yeah.
But you know, I consider distributed biotech when it's distributed to people who normally wouldn't use it. So, I mean, Suzanne, is there any corner of your world that you haven't seen it penetrate yet, but you would like to see it penetrate into? Or, you know, you've been approached by all these huge companies, Adidas, Nike, the things that you showed, the North Face and Omega watches. Are there any companies that you think are going to see that Kodak moment where that's sort of a cautionary tale in business, the way Kodak rejected digital photography?
I actually think it's the opposite.
You don't have to call anyone out.
No, but I think, you know, so, you know, while a lot of people may still be just hearing about these technologies, and certainly, you know, there's still a very limited number of startups really, you know, investigating these materials and trying to bring them to market. There's very few things out there. And that leads you to assume that actually there's still a lot of work to be done to get, you know, more in the sort of broad consciousness of consumer brands sourcing materials. The reality I found over the last 5 years or so is that all of the big players have been pursuing the very small pool of innovators in this field. And a lot of them have developed biostrategies for how they want to transition away in time from petrochemical sourced ingredients to bio-sourced ingredients. So actually, I think it's the converse. It's actually surprising just how many people not only are aware of these technologies and really pushing for them to come to market faster so they have alternative choices to what is currently on offer. And it's a competitive environment. And I think there's a lot more to say around that, especially on, you know, IP and who owns it and what that actually does for the next generation of innovators. But I think it's more than we've got time for, unfortunately, on this panel.
Yeah. So Mitch, you're going to get the last word. What is the city of the future going to look like with this biological incorporation? Is there? I have this sort of Jetsons like image in my mind, as we all do. Sort of science fiction informs that, but
yeah, I love the Jetsons. I think I love Rick and Morty a little bit more. But yeah, there, you know, somewhere I think there was a title where we're going to talk about growing cell phones. Or something to that effect, and that was super intriguing. I thought
from Drew, so
yeah,
I didn't.
Okay, love the title. You know, I'm thinking like, but that is part of the issue. Like, what would a cell phone that's grown be like? Because it's something that is inherently important to so many of us, especially in the developed world. It should be for everyone. But a cell phone that's grown. Now, the first thing that came to mind was what Elon Musk is doing with Neuralink. So he has you know, it's now not available on a wide market scale, obviously, but it's available to certain patients that have muscular disorders. But essentially, it's they take out a section of your skull and they implant more or less elements that make up a cell phone that react instantly with your thoughts on some level, which sounds like science fiction. Honestly, but it helps control some of your motor functions. And then later on, it actually integrates in with your speech and your visual output. to where you can imagine a world, and this is very Black Mirror, which I kind of like, except for the dystopic part of it, where you can actually speak to someone with not moving your lips, just look at each other, and we use our cell phones that way. And I'll be the first one to reject that product when it comes out, I guarantee you. But I can imagine being on a faculty meeting at NYU where I'm missing out because no one's saying anything, but they're saying something to each other. And I guess on that note, what we also didn't touch upon besides education, which we just now covered, is fictive narratives. We don't have a science fiction author here, but so much of the things that influenced me and so many people I know comes from that sort of culture and class where people write in detail an idea of the near future, whether that's a city or a cell phone or anything in between. And they get down to what life would be like with that type of new instrumentation, that new type of biotechnology. And I think that's important to run those scenarios as stories at first, because we can tease out what we need to really worry about, where the real precautionary principle needs to be applied. And then we could also sort of incentivize or excite others to get involved in this kind of future so that they can be on board because they know where it leads and they know how it integrates to everything else. Jules Verne was a great writer. He imagined going from Earth to the moon, and he did that 2 centuries before that was possible. All those people that went into aerospace engineering at NASA, most of them read Jules Verne. It was a dream, and dreaming in detail, not promising, because I think that's wrong, but dreaming in detail, I think is super helpful to get us into that next level, this synthetic biotechnology civilization 2.0 that we've got to get to. And that could happen across almost any field. So I really kind of feel that's a strong direction.
That's a super good point, Mitch. Well, we've got to come to an end. I could talk with you guys all day. Thank you so much for joining me and joining DLD in this presentation.